Hi everybody, my name is Min Yuan, and I am a student currently working on master degree at the Southeast State University. Today I'm gonna talk about a research paper. The title is Cloud-based data storage and visualization tool for smart city IoT, flood warming as an example application. I'm gonna explain the paper in four parts, as the slide showing there. Before I dig into this part, I'm gonna firstly talk about the introduction of this paper. A recent advance in information and communication technologies are enabling IoT smart city projects to collect and analyze the vast amount of data in an effort to support more environmentally and economically sustainable communities. For instance, smart storm water projects have shown successful IoT-based infrastructure monitoring applications to address communities' operation and planning challenges. As IoT devices become more pervasive, the collected data is expected to play an increasingly central role to inform communities' decision, and therefore it is critical to develop and maintain cyber infrastructure to collect, store, and visualize the sensor data. So let's kick off the first part, the main contribution of the paper. So the main contribution of the paper are providing practical insight on the development of cloud-based tools for IoT applications, addressing an emerging area that is often overlooked in empiric IoT research, proposing a general cloud backend system architecture to guide IoT developers to in quickly prototyping smart city applications, utilizing tools such as serverless data injection for IoT historical backup data storage, on-demand MyCircle database and Grafana servers and RESTful API for programmatical data access. Performing a cost analysis for the initial years of using AWS cloud servers in an IoT application, highlighting the cost effectiveness of the proposed solution and offering IoT developers a cost estimate based on various number of sensors and data creators. This research paper is to solve some primary problem. The primary problem discussed in this paper is the challenge of developing and integrating hardware and software solution for IoT smart city projects. So this task require extensive specialized knowledge in various ICT DOMs, which can be done for IoT system designer. And the paper focuses on simplify IoT system design efforts by utilizing open source tools often provided by the Science Network and creating a scalable cloud-based infrastructure for data storage, visualization, and alarm notification. At this part, I'm gonna explain the solution proposed by the paper. The solution proposed by the paper involves the use of hybrid approach that integrates both classical and quantum machine learning techniques. This approach aims to enhance the overall performance of the machine learning model by leveraging the strengths of each type of computation. And specifically, the paper suggests the following key components in their solution: quantum feature mapping, and utilizing quantum computers to transform input data into a high-dimensional space. This process helps in capturing complex pattern that might be challenging for classical algorithm to detect. And the second is hybrid model architecture, combining classical narrow network with a quantum circuit. The classical part handles the data pre pre-processing and the initial feature extraction, while the quantum part focuses on more intricate pattern recognition tasks, optimization and training, and developing novel algorithm for optimizing the hybrid model. This includes adjusting parameters in both classic and quantum components to minimize the loss function effectively. So the last one is performance evaluation, implementing a robust framework for evaluating the performance of the hybrid model against the classical only model. This involves benchmarking on standard data side and exercising improvement in accuracy, speed, and resource effectiveness and efficiency. By integrating those components, the paper proposes a comprehensive solution that aims to explain the advantage of quantum computing in practical machine learning applications, potentially leading more powerful and efficient model. So this slide just explains the outline of the paper. So in the next part, I'm gonna talk about more in detail with the diagram. As the picture showing there, this is a very detailed workflow picture. So our cloud-based system is designed to efficiently manage and process sensor data by leveraging a range of advanced AWS services. The architecture utilizes AWS Lambda for serverless computing, and Amazon S3 for data storage, and Amazon API Gateway for interfacing. And computing instances are handled by Amazon EC2, which are start on demand to optimize resources usage. A Passion script is employed to ingest historic sensor data on virtual machines that are, where another script connected to our application's TTN and QTT broker for real-time data injection. Those injection data is then queried and visualized through Grafana, offering robust monitoring and alerting um, cap- capabilities via a graphic user interface. For structured data access and dashboard monitoring, MyCircle and Grafana EC2 instance are activated as needed, ensuring efficient resources management. Additionally, our system provides a RESTful API for programmatic data downloads, enabling users to perform data analysis in Jupyter Laptop or modeling tasks with the stormwater management model. And we also host static softwares using Swagger UI to document the API interface, providing users with direct access to data downloads. Although no explicitly depicted simulation and modeling tasks are assumed to be conducted by users on their own servers, which could be hosted on an EC2 instance in AWS, other cloud provider, or their local machine. This flexible, scalable system architecture ensures comprehensive support for a wide range of data processing and analysis needs. So finally, this picture is S3 storage usage. As you can see, the different devices and the different TAN word shows the different speed to increasing. And where data collected by IoT smart city application are central asset in supporting management and planning decision for many communities. Designing and deploying IoT solutions is still challenging due to system integration complexity, reliability limitations, and the cost. We present a cloud data storage and a visualization system for smart cities, leveraging reliable existing technology to integrate a computer and complete IoT monitoring solution hosted in AWS and hosting under USD and 26 per year for long-term data storage and USD 0.0204 per hour of use for MySQL database and Grafana servers. By using this cloud-based solution together with TTN infrastructure and commercial LoRaWAN sensors, users can collect, store, and virtualize data set to address their needs and integrate their own servers. We demonstrated the usage of the system for the flood warming system application example with river and weather and LoRa LoRaWAN sensors. The cloud-based system design use serverless data injection to provide a simple and cost-effective data storage solution, that is independent of and other services such as data visualization and on-demand database and visualization servers offer flexibility to adapt it to application. It's where saving cost and simplifying maintenance of operations. Furthermore, we explore the different AWS tier and their respective reliability cost trade-off so users can make an informed decision when tailoring our system to their own application, as opposed to focusing mainly on the example application as commonly seen in the literature. We highlight the common taskers that are required by an IoT project and share our insight in leveraging modern cloud servers to simplify IoT backend system design and optimize cost. As a future researcher and venue, we intend to explore the use of new serverless cloud backend architecture in smart city IoT applications and investigate practical trade-off to server solutions. We intend to analyze in particular the on-demand allocation of computation resources as we scale the numbers of sensors and total sensor data rate and the number of clients connecting to a user's interface in cloud IoT backend system. We also intended to explore the integration of modeling and simulation tools with IoT data equation and system. We are effectively allocating um, computational resources